hello everyone. Thank you for your time and welcome to our webinar today focused on how to achieve operational excellence for batch processes. I am Larry Gukombi. I'm a digital asset consultant working for IPCOS. Before we get into the presentation of today, I would quickly introduce IPCOS and what we do. IPCOS is a service provider with unique expertise in the process industry, providing a full value chain of projects, so right from consultancy to delivery and support. We currently have 7 offices worldwide with a long-standing professional reputation of more than 25 years working all across the globe with our clients. IPCOS is now part of a bigger group of companies called PA Solutions, which operates in key industries ranging from chemicals to automotive to pharmaceutical to the energy industry. Focusing specifically on what IPCOS does, IPCOS expertise aims to facilitate the needs of users and their use cases. So be they a manager, a field operator, an engineer, we work with our clients towards optimization, ease of communication, performance monitoring, and specific use cases pertaining to the needs of a specific user. IPCOS also partners with technology players across all levels of automation. We have worked and still work with partners including Microsoft, AWS, Aviva, AspenTech. IPCOS also has its own proprietary software pertinent to our advanced process control side of the business. With our reach across continents and in the process industry, we have clients cutting across industries such as refining, petrochemicals, specialty chemicals, and so on. And these are the industries where batch processes exist. And today's webinar will be focused on the steps towards achieving operational excellence in these processes. So I'll be giving the opportunity to Christian Mons, who is the sales director of IPCOS, to present the webinar of today. Christian has a background in control engineering and has been working in IPCOS right from the start of the company, as he is also a co-founder of the company. He has 25 plus years of experience in the process industry working on topics including advanced process control, process optimization, and consultancy. Also, we'll leave some time for Q&A session at the end of this presentation today, so please feel free to type in your questions and we'll get to them after the presentation. So over to you, Christian, and we can get it going.
Okay, good afternoon or good morning, everybody, depending on where you are in the world. Today, we are going to have, as Landre said, and by the way, thank you very much, Landre, for the introduction, about optimizing batch reactors. Yeah, so not continuous, but today it's all about batch. Yeah, as a service company, IPCOS has already been working a lot in the batch business. Yeah, let's call it like that. For different kind of companies, and you see there a couple of names, specialty chemicals, but you also see pharma names over there, which in fact impose a couple of extra constraints on how you can optimize, and even if you can optimize these kind of processes. Very often we work in the batch industry on base layer optimization, because there is still a lot you can do at that level. Yeah. And then at the second level, you can talk about model-based predictive control, APC. There are 2 flavors of APC in batch, and we're going to discuss about that as well. Yeah, and one other domain that we are very active in the batch industry is regarding industrial digitalization, and that is typically for companies like Arkema, Solvay, and Röhm that we do that. So bringing all the data together, and having things like OEE, data integration, KPIs, and so on, which help to measure, in fact, if you're doing a good job when you're optimizing batch reactors. Good. Now let's start with the basics. Why APC and optimization has been so successful for the last, I think, even 50 years almost, in companies, well, in refineries and ethylene crackers and ammonia plants and power plants and so on. And why don't we have that much success stories if we talk about high-end optimization in the batch industry? Well, because the answer is because batch has some particular properties which make them, on one hand, extremely easy and extremely simple, and on the other hand, extremely complicated. So let me elaborate a little bit on that, because based on these arguments, you're going to understand why certain things work and other things don't work. Yeah. So first of all, let's start with the good news. Yeah, batch reactors are extremely simple. Yeah, there is a reactor, there is a jacket, yeah, or there are coils around wounded around the reactor. There is an external heat exchanger, a top condenser sometimes, yeah, and a mixer. And then basically we have covered, I think, 99% of all the batches in the world. Yeah. Some of them have a couple of heat exchangers and so on, but basically with these 5-6 extra components, you can build almost any batch application that exists. Yeah, so that's good news. It's very simple, but of course there is also one negative aspect on it. There is not much you can do. Yeah. You can play with the stirrer mechanism, although I don't see that very often, but you can also play with the external heat exchanger, so the cooling and the heating, yeah? And the feed, if it is a fed batch. A fed batch is in fact a batch reactor where while the batch is running, you feed new material, yeah? But for a pure batch, and a pure batch is something where you say you put everything in and then you close the lid and then everything starts to react. Even that degree of freedom doesn't exist if you have that kind of batch reactors. Yeah? So almost nothing to play with besides some heating and cooling and perhaps some feed. Yeah? That also means that you have hardly any measurements. Yeah, pressure. Well, most of the batch reactors run at 1 bar, so that is even very often not available. But you have a couple of temperatures. Yeah, cool water temperature, steam temperature, or hot water or hot oil temperatures. You have what goes into the jacket and what comes out of the jacket. So based on that and perhaps a flow measurement, you can then estimate how much energy you sent into the reactor or you pulled out of the reactor. Yeah, so a couple of temperature measurements. That's typically what you have. Now that's the good news. Huh? It's very simple. But now, what other properties do batch reactors have that makes these extremely complicated to work with and to optimize? Is that you have many different products. Yeah, so in one batch reactor, sometimes customers make 10, 20, 30 different products during the year. And if these products are extremely different from each other, yeah, that means that every time you want to optimize a batch, you almost have to start from scratch. Yeah, you have to model it, you have to optimize it, and so on and so on. So for every individual product, you have to perhaps do a full optimization project. Yeah, and if you have 10 or 20 products, that means that every product runs only once, 1 month per year or 2 weeks per year, and the whole investment of optimization has to be paid back in that 2 weeks to 1 month. 1 month. Yeah. So that is something that is very specific for batch reactors. Yeah. So very often there is no one solution that fits all, that you say, well, I'm going to have one optimization strategy, one model, one set of PID controllers, and everything I make during the year can be optimized with that. If you are in that situation, you're just lucky. Yeah. And that is why sometimes you have to start what they call clustering. And what is the idea there? Well, you say we have 20 products, yeah, and these 3 over here are so much similar that if we optimize the production of these products in this way, yeah, that should work for all these 3 products. And then you have 4 others, and there also you can say, well, if we optimize the recipes and so on for these 4 products with one solution, okay, we can cover them. And so with 2 solutions, you then already cover 7 out of the 20 products. So that already helps. That's called clustering. Yeah. One extra problem is that the product quality, and that's the proof of the pudding is in the eating, as they say, is at the batch end. Yeah. So when the batch is finished, then you know if you have done a good job, yes or no. Yeah. So there is only one measurement, in fact, and that's at the end. Yeah? We'll come to that later. Detailed knowledge on the chemistry is often not available. That's indeed the case. Yeah. So the main reactions in a batch reactor, of course, they are known because the product and the process was developed and invented and patented and so on and so on. So the main reactions are definitely known. That's a no-brainer. Yeah. But if you talk about side reactions, and typically that are the ones that have a negative impact on the quality, that's another story. Very often nobody knows about these side reactions. Or at least you know that they exist, but you do not know how intense they are. And the more intense you have them and the more of these side reactions, very often the lower the quality is. So, and there often you have no clue what happens really in the reactor. Yeah, that is why people very often then jump into things like black box modeling. Yeah, so based on neural nets, AI, and these kind of things. On the other extreme is first principles, where you really write down every chemical equation and so on, Arrhenius laws, you use everything you have. I only know for the last 28 years I've been doing this, one company who has provided us these first principle models of their own batch reactor. Yeah. And then you have hybrid, where you say, well, you know, the hardware is known. I can model the hardware, the jackets and the coils and so on. But the reaction part, I have no clue. So I'm going to model that part based on black box. And based on first principles, I'm going to model the hardware. That's the hybrid modeling. Yeah. For certain processes, it is even not allowed to do optimization. Yeah. If you talk about pharmaceutical processes, changing the recipe online, yeah, is very often just not allowed at all. Yeah, so there are regulations. You can optimize it once, then you have to do all the certification, and once the certification is done, the optimization is okay, certification is done. From then on, you stick to that new recipe. But having online stuff that then manipulates recipes and in order to speed up reactors and so on in the pharmaceutical industry, that is, I think, always a no-go. Yeah. A batch never reaches steady state, yeah. So it always is on the run, yeah, and it's only at the end of the process that it stops, yeah. So the behavior always changes, yeah, and it is also very nonlinear, especially fed batch reactors. You start with an almost empty reactor with 100 kilograms of material. And at the end of the reaction, which is 5 hours or 20 hours later, yeah, you end up with 60 tons of material. So believe me that the dynamic behavior of that process is very different, 100 kilograms compared to 60 tons, yeah. And that you see here in this bottom window over here, that the dynamic behavior as just simple PID tuning, yeah, you tune it for steady state operation, whatever that means in batch, yeah, and you see that at the end of the process, the PID behaves reasonably well, whatever that means, but it's definitely clear that the PID tuning is very bad for early batch conditions. Yeah, so when there is almost no material in there, and that's why you see that it starts to oscillate, and gradually, when you have more material, that everything becomes more and more stable. Yeah, so all nasty properties of batch reactors, which makes it extremely difficult, or let's say much more difficult, to optimize them, although from a distance it looks like very simple processes. Good. And then, of course, everybody wants to have the golden batch. Yeah? And the least what an optimizer should do is promise you and realize that every time you run the batch, you follow the golden batch. Yeah? The golden batch is the best batch you have ever achieved, and really achieved, and not in theory, but really done, executed. Yeah, during the runtime, so that the runtime of your equipment. Yeah, and if you can already make sure that your optimizer or whatever you have repeats that golden batch on and on and on again, well, then most of the people are already extremely happy. Yeah, so that's at least one thing that we should do with optimization. Yeah, and then you can even go one step further by saying, well, the golden batch is not the ultimate batch. There is, let's call it a diamond batch, yeah, which is even much better, which is faster, better quality, and so on and so on. And that will then become the new golden batch when we achieve that. And from then on, that golden batch will be the new standard. So we're going to do everything we can to repeat that golden, or that new golden plus batch, if you want to call it like that, yeah, from now on and on again. So, and we have different ways to do that. Yeah, golden batch monitoring, we're going to talk about very briefly, intra-batch optimization and inter-batch optimization. Now, if you want to do optimization, then of course it is important to measure how good or how bad you are actually performing or your batch. Yeah, and OEE is one of the methods which is very often used. Yeah. So, and you have OEE monitoring tools where you see here, for instance, you have so many hours or so many minutes or seconds in a day. Yeah, and based on the graph here, you can see how much % of that day was really that batch producing the right quality. Yeah, because sometimes it produces, but the end result is a bad quality. So that means that a part of the time that batch was producing something which is bad, meaning it was not useful, that batch run. Yeah. So, and that is something that we as ITCOs also provide to our customers, these OEE, integration services, because the idea is, first of all, that you bring all your data together from one unit, from multiple units, from one site, from multiple sites, yeah? And you do it as such that it is automated as much as possible, that you don't have to rely that much on operators to fill in forms and so on and so on. So there are systems which help you to automate the OEE dashboarding and KPI calculations as much as possible, so that you don't have to rely that much on people to fill in forms and so on, because that means sometimes they will not do it, they will not do it accurately and so on. So try to do it as automatic as possible. That will give you the best overview and also the fastest overview, because you want to know exactly what happened today or last hour, and take decisions based on that. Yeah, so we can help you to build your OEE solutions so that from now on you can monitor how good or how bad your batches are running, and when optimization is done, that you can really see the influence of optimization on the runs. Yeah, good. Different ways to optimize a batch run. Yeah. So I have about 3 categories, let's say, yeah, and one of them is the least invasive, is what we call the golden batch monitoring. Yeah, so you have your golden batch. We have not changed it yet, so the golden batch is defined from the history. Yeah, and you have a sort of, well, let's call it an envelope around your recipe, for instance, and you say or you monitor if your current batch, yeah, follows or stays within the envelope around your golden batch. Yeah, it is the least invasive monitoring system, because it just tells you you're doing a good job or you don't do a good job. Does it already help? Yes. Because assume halfway your batch, yeah, you get an indication that, well, you don't follow the envelope anymore, or you're drifting away from the optimal recipe, let's say, yeah, then as an operator, you might still intervene and do some corrective actions, if that is possible, if you know what to do when something happens, yeah. And worst case is that you say halfway the batch, yeah, let's stop the batch because this is going nowhere. I'm going to save 3-4 hours of batch reactor time, because I know that if I let it run, that it will finish in 3-4 hours, but the quality will be waste anyway. So it's better to stop it now. Yeah. So that's the least invasive method of looking at your batch reactor. Now, of course, what we are all want is to optimize it, make it better, yeah, so that quality is better, it's faster, and so on and so on. And there you have different flavors. First of all, follow the recipe as good as possible. So what does that mean? Is you have your recipe, you haven't changed it, but from now on we're going to follow it very, very strictly. And the idea is that if you follow the recipe without too much errors, that always results in at least good quality, repeatable quality, and so on. Yeah, that's already a big challenge in batch. Yeah, although it's okay, that's a no-brainer. Well, it's quite sometimes difficult to do. Yeah. Secondly, yeah, is run as fast as possible. So there, the idea is that you instead of 5 hours batch run, you go for 4 hours or 4 hours and a half. Yeah. And there you have 2 different approaches. Is there where you say, I'm going to push the batch reactor to the limit, and that's typically cooling or heating limits, or safety limits, yeah, knowing that by doing that, you have no impact on the quality. So if you push to the cooling limit and the quality is still okay, then you can speed up the batch. Yeah, that's the most easy way to optimize. Next level is that you say, well, I'm going to push my batch to the limits, but knowing that by doing that, I'm going to impact the quality. And typically you're going to impact it perhaps in a negative way. So I have to hit the brake here and there, so that I can always guarantee that my quality at the end, not during the batch, because most of the time you have no clue, the quality at the batch is, at the end of the batch is still okay. Yeah. That's called intra-batch. So we're going to do something during the batch. Yeah? And then you have inter-batch, where at the end of the batch, you say, what have we done? And what can we now learn for the next batch if it starts, to do it better. Yeah, there are also a whole bunch of assumptions that we have to make there, but I will come to that later. Good. Follow the recipe as good as possible. Yeah, and that's typically something that is the job of PID control. Yeah. So first of all, you have to do an optimal design of your controllers. Yeah, and then you have to do optimal tuning. Yeah, optimal design means it is very nonlinear, a batch. So valve linearizations, because especially with fed batch, you start with valves which are hardly open, 5%, 10%, because you need hardly any cooling. And then when the batch is full with 60 tons, you need a lot of cooling, so that valve is going to travel from 5% to 95 or 100%. And of course, a flow controller can do the job, but in certain conditions, you have to do some valve linearizations. Split range. Well, why is that important? Well, if you have temperature control where you heat, for instance, with cool water, with hot water, and you cool with cool water, yeah, it might be depending on the delta T of the reactor temperature compared to the cool water, or the reactor temperature compared to the hot water, that the gain is different. So the impact of opening a valve of 1% on the cool water side might be much, much bigger than the impact of opening a valve on the hot water of 1%. Yeah, and a PID controller doesn't like that. Yeah, and good split range control design, yeah, helps you to overcome that. Yeah, this is an example what you see over here. I don't know if you can see the arrow, yeah, the pointer here. This is a batch reactor, for instance, where you see continuously a change from cool to heat, cool, heat, cool, heat. Yeah, so the temperature control was rather okay in the sense of temperature was following the recipe. Yeah, but this is a disaster for your equipment. Yeah, so you heat it up with 180-degree oil, it was, I think, in this case. Yeah, and then 10 minutes later, you're going to cool everything down by 20-degree cold oil. Yeah, so the thermal stress on your equipment is dramatic. Yeah, so the quality is okay, but you have leakages every week. Yeah. Now, so by just doing simple tuning, yeah, then you can change this to this picture over here, where you see initially, well, the colors are wrong, but initially we're going to heat it up. That's this kind, and from then on we're going to cool it with this. Yeah. So thermal stress is much, much lower, and the quality of the temperature control is almost as good as before. Yeah. So that is why you, with some simple tuning, you can really make a big difference. Yeah, feed forward. Yeah, for instance, here you have your temperature profile, your desired temperature profile, and here you have your turn from increasing temperature to flat. Yeah, and now if you know this up front, you might tell your PID controller, well, you know what, in order to avoid overshoot, you better hit the brake somewhere over here, so that from now on, the overshoot will be minimized. Yeah, that's a matter of design by using feed forward, good tuning, and so on. Yeah, all things that you can do at base layer level. Yeah, and then you have to do the tuning, of course. Yeah, and the key word for batch PID tuning is robust control. Because, well, it is so non-linear. You start with an empty reactor, you end up with a full one, or you with pure batch, you start with 60 tons of almost something which is liquid like water, and you end up with something which resembles glue. Yeah, so the heat exchange and the heat transfer is completely different. So the gains and so on are very different. So you need to have a controller which is extremely robust. Yeah. And you can tune, yeah, we can help you to tune controllers that are extremely robust. And that's what you see here at the bottom, yeah. This is a controller that we tuned, and you have a set of parameters that cross over here, yeah. But assume now that the gain of my process is double the one that I guessed initially, yeah. Well, then we still want the process to be stable. So then we jump to here, and the controller still has to be stable. Assume our gain is 4 times bigger than we assumed, yeah, which is quite a difference. Then still the controller needs to do stable control. Yeah, of course the performance will be lower, but at least it's stable. Yeah, same with delays. If there is 1 minute extra delay compared to what you had in mind, well, it should be stable. And the combination of gain errors and delay errors should also be stable up to a certain level. So robust control is key. Yeah. So trial and error tuning for batch is very often not very successful. Yeah. As I said, deal with nonlinearities, not too nervous control. That's exactly what you have over here. Handle inverse response. Yeah, what is that for fed batch, for instance? If you have a reactor which is at 100 degrees, so what's inside the reactor is 100 degrees, and your feed material is at ambient temperature, 20 degrees. Yeah, so when you throw new material in, yeah, you have material of 20 degrees which end up in a reactor at 100 degrees, so it will cool down the reactor a little bit before it heats up and then takes part of the reaction and then even become exothermic. Yeah. And of course, if you throw in 20 kilograms at 60 tons, nobody knows. Yeah, it's even not measurable. But if you throw in 20 kilograms of material on a volume of 100 kilograms, the effect is huge. Yeah. So, and inverse response, yeah, is something that explains that behavior. Yeah, and now you can tune your PID controllers to deal with that. Yeah, that's called a non-stable poles, non-stable zeros. Yeah, so but you have PID tuning software like our RTO Tune and PID tuner who can deal with that. Yeah, optimal disturbance rejection, especially if PID, so if heat exchangers and talk to each other. Because sometimes you have a hot water circuit and a cold water circuit, and you have a whole bunch of batches connected to it. And if the hot water or the used water from one is entering the other one, then these reactors, they're going to talk to each other through their cooling and heating system. Yeah, and that is disturbances that you might have to deal with PID control. Yeah, so quite already a challenge that you have, and you have to do some optimal PID tuning. Yeah, so first of all, use the proper DCS template. Yeah, if it's a Siemens or a Rockwell or Emerson or the Honeywell, whatever, tell your software which kind of PID template you have, because that makes life easy. Yeah. If possible, that's what we ask our customers, but it's not always possible. But we try to convince them to go first for water solvent batch runs. Yeah, so where not the real products are in there, but some water or water combination with solvents, so that we can do proper tuning based on that. Is as good as it gets, because it's not the real product, but okay, yeah, it's better than nothing. We really like to apply step tests in open loop, yeah, and with a decent signal to noise ratio. Operators don't like that, but sometimes, well, no, it has to be done. Yeah. Plan B is, of course, that you can do closed loop testing, which is much more difficult. It's not that you throw closed loop data into a PID tuner and, of course, a model will come out and a tuning will come out. Will that be the right tuning? Well, that's the big question. Well, in fact, it's not a question. The answer is no. Yeah. So closed loop step testing, watch out for it. Yeah. We're working on this in our new PID tuning tools to do to be able to deal with closed loop data. Yeah. It will be released, but it's not there yet. Yeah. So what you always can do is when the batch is finished, yeah, so it has run for 5 hours, yeah, well, and then you have a whole bunch of material, 60 tons or 20 tons or whatever, in your reactor, well, you can perhaps apply a couple of step tests then, yeah, so heat it up, cool it down, heat it up, cool it down, and at least it gives you an idea on the dynamic behavior of your process when the reactor is full, yeah. So at the end of the process, you might do some extra tests in open loop, yeah, which will help you to tune your controllers. Yeah, and then of course you have to tune them, make them robust, limit the overshoot, undershoots, and so on and so on. Yeah, the benefits of these things are huge. Yeah, so you reduce the variations of quality, of temperatures, and so on and so on. And typically, when you reduce the temperature variations, you very often end up with better qualities. Yeah, so here you see an example. Yeah, so it is a fed batch. Yeah, so this is the feed. Yeah, and this was the original temperature profile, and the set point is the red line over here. And by doing some PID design, tuning, and so on, we came up with that blue one over here, which is definitely much better following the set point than the pink one. Here at the bottom, you see the same thing. This is a batch, I think, in pharma, yeah, where you see the blue line here is a set point, yeah, The green line is, in fact, the tuning as it was before. A huge delay, meaning that the controller is extremely slow. And then, of course, the integrator says, "Ooh, what's going on here?" So he starts to ramp up, and then you end up with overshoots, of course. Yeah. Decent tuning is the red one. Yeah. Immediately when the set point changes, you follow and you level out without any overshoot. Yeah. And that very often results in better quality, more consistent quality, less alarms, less operator interventions, and so on. So, and repeating your golden batch on and again is very often what you that you will get by doing this. Yeah. So definitely a step that you cannot overlook when you think about optimization. Now, let's go one step further. Run as fast as possible by pushing the unit to the limits with no quality constraints. What does that mean? So, in fact, you assume that you have cooling and heating limits, yeah, and that you're going to feed typically as fast as possible. So you're going to change the recipe in this case, yeah, and you're going to push to these limits, and you assume that it has no impact on the quality. Okay, that is a very serious assumption, but okay. Now, what is the advantage if this assumption holds? Yeah, is that in fact you can consider your batch reactor as a changing continuous and linear unit. Yeah, you only have to look a couple of minutes in the future, yeah, or 10 minutes or so, yeah, depending on the batch run. Okay, but let's say 10 minutes in the future. Yeah, so it is the principle of receding horizon, what you typically find in classical APCs. Receding horizon, you look into the future, and then you're going to anticipate disturbances and so on and so on, in order to optimize your cooling and heating, or cooling and heating. Yeah. So a standard APC can do the job. Yeah, you only have a few handles to play with. Yeah, the feed and then also play a little bit with the heat exchangers. Yeah, so there's not much you can play with. Disturbances, of course, is perfect to deal with a classical advanced process control. And the nice thing is it's a very small APC. There's almost nothing to play with. A couple of MVs, you have 2 MVs, 3 MVs max. Yeah, you have hardly any measurements. So a very simple small controller can perfectly do the job. Yeah. Of course, we're going to change the recipe in this case. We're going to feed faster. We're going to change the temperature profiles and so on. So yeah. You can already impose a couple of constraints regarding quality, in the sense that if you know, for instance, the temperature should never exceed 120 degrees, or the rate of change of the temperature should not be faster than 5 degrees per minute. Yeah, or I don't know what. So T error is the error, is not a terror, but so the maximum deviation from the temperature from the set point should never be more than 1 degree, or I don't know what. These kind of constraints, if you can impose them to your APC, and then you say, if I can comply with these constraints, I'm sure my quality is okay, then you can even impose these kind of constraints, which is good. Yeah. So it's a very simple solution known with standard APC technologies. Yeah. So it's a rather cheap solution which can do the job. Yeah. So here you see a scheme, yeah, where this is just a drawing, yeah, but then you can see the principle. So you have a standard temperature profile. You have your cool duty. So the red line here is the cool capacity that you have available. Yeah. And this is the feed flow, and your quality should be under this line, so the quality is okay. So what are we going to do? We're going to push the plant to the limits, yeah, the cool limits. Of course, we're going to feed faster. Quality might degrade a little bit, but still perfectly acceptable, yeah. And that's what this APC is going to do. Here is an example, a real life example, where you see the inlet temperature of the jacket, yeah, from the batch reactor. So the cool water is at 20 degrees, yeah, and the inlet temperature fluctuates around 25 degrees. So there is a part of the cooling water that always goes around, yeah. Now, of course, what is the maximum cooling capacity that you have if you only supply fresh cool water and almost nothing comes back, yeah? So that means that if you see that your cool water temperature, the inlet temperature of your jacket is close or at the cool water temperature, that means that you consume or that you use all the cooling capacity that you have available, which allows you to speed up the batch reactor. And that's what you see over here. You see that the cool water, so the inlet temperature of the jacket is almost always or very close to the cool water supply temperature, yeah? Which means you did whatever you could to speed up the batch reactor, and the quality is still okay. So that's what you see, for instance, here as well. Huh? So the old feed recipe is like this, yeah, and this is the new one. Yeah, you see that you feed faster and more, yeah, temperature profile, and then you can add, for instance, an extra constraint, which is the critical reactor temperature, and which is a hard constraint, never exceeds this blue line over here. Yeah, and you see that the APC controller perfectly complies with that. Yeah, so that's the most easy APC type that you can apply on a batch. Yeah. And now the most complicated one is where you say run as fast as possible, but by pushing the unit to the constraints, I'm going to hit my end quality constraints. And I cannot tell you at this moment, yeah, that by just simply looking at the maximum pressure or maximum temperature or a deviation, that will have a quality impact, yeah, or no quality impact. No. What you have to do now is that you have to have a model between what you are doing at this moment and the end quality. Yeah, and that can be a quite complex model. So you have to look at your batch as something where the APC always looks until the end of the batch. When I'm doing this is going to have my impact on my end quality. Now I'm going to increase the temperature a little bit. Oh, my end quality, the density, the color or whatever is going up, and that's not allowed, so I should not do this. Yeah. So you have to have a relationship between what you're doing now, and even more what you already have done, what you tend to do based on the recipe probably, and then the impact to the end quality. And that is something completely different. Yeah. And you need other tools and other technologies to deal with that. Yeah. So because, as I said, you need to have a quality model between process conditions and end quality. Yeah. And that in an environment where I don't say nobody knows what's happening in the reactor. Well, but yeah, it's partially true, because you're going to trigger side reactions, which will have an impact on your end quality, and you have to find a way to model how many side reactions are going to happen, and what kind of effect are these side reactions going to have on the end quality, and so on. Yeah. Excess product is typically a parameter that can help you to, I don't say it is the only solution, but that can help you to explain that. Yeah, excess, what is that? That are in fact a whole bunch of molecules which have not reacted yet to form the end product. They are the guys who are the free birds swimming around in the batch reactors, and they have not found any friend yet to form an alliance with. Yeah. So the problem is that the more of these excess, so these free guys that are swimming around, the more side reactions might start. Yeah. So that is sometimes a parameter to control, where you say, I'm not going to feed too much, because then there will be more and more excess product in my reactor that will trigger side reactions. So there will be a sort of limitation on the amount of feed based on the estimation of the excess and the relationship between the excess and the end quality. Not very easy to make. Yeah. So you will end up with continuous models. Yeah. So first principle, black box. You might use historical data, but watch out, you might need a couple of extra test runs. So you're really doing a full-blown nonlinear APC project. Yeah. And of course, the recipe will change during the batch. Yeah. Now you can do it in two ways. Yeah, in open loop means you're developing that technology, you're making all these models and so on, and finally you will come up with a new recipe. Yeah. So in fact, well, the thing is, this is how I'm going to feed during the batch, and this is the temperature profile during the batch. Yeah. And if you do everything offline, and when you have done all these exercises, you end up with, okay, this is the new recipe, so this is the new feed profile, and this is the new temperature profile. Yeah. And then from then on, you program it in your DCS, and you let your DCS with the PIDs do this kind of job. It's not fully optimal, because because disturbance rejection, well, you can't hardly do that, because while you were developing this system, you could not take all the disturbances into consideration. Yeah, but you might perhaps already go one step further compared to your golden batch, make a new golden batch or a better golden batch, which is in fact implemented in the recipe manager. Yeah. Now, of course, the cherry on the cake is the closed loop. where in fact that optimizer really changes every time your batch recipe completely. Yeah. But therefore you need the Rolls Royce under the APCs, the full-blown nonlinear, and so on and so on. Yeah. There are not that many solutions on the market as we speak today. Many of them are still in the proof of concept phase. Yeah. So what are typical the benefits of this? Well, I've seen a couple of them, but I think we can't really say that there is already enough data to say, well, typically this is what you're going to end up with. I have a couple of numbers, but it's not that I have a huge amount of data points to say the benefit will be such and such. Yeah. So there are at this moment, depending on which vendor, a couple of strategies that are used. Yeah, one is where you say we have a couple of milestones we define. Yeah, and you can make as many, well, not as many as you like because it will complicate the approach. But you define a couple of milestones. Yeah, and then you make a model between what happens at that milestone and the batch end. Yeah, so you have here a model between this point and the end quality, between this point and the end quality, and so on. That's the most simple, based on black box, principal component analysis, the AI, and so on. The next level is that you say, I have these same milestones, yeah, but I'm not only going to look at the condition in this point, I'm also going to look in one way or the other. I'm going to lump the history between this milestone and this. So what have I done here, or what happened in this area over here? I'm going to use the conditions over here and what happened over here to estimate the end quality. Yeah, so that's a little bit more complicated. Well, a lot more complicated, but that's the next step. Yeah, also black box data driven. Yeah, and then the most complicated one, yeah, ways where you have at every minute, second, or whatever, you have a whole model that really takes everything into consideration, like in the linear APCs that you find in refineries. At every instance is going to predict what have I done, what's going to happen, what's the end quality, and so on. Yeah, so this is the most complicated one. I have not seen really black box solutions that are able to do that. Yeah. Very often people start looking into first principles, yeah, and that also means that you typically are going to look for certain amount of batches which are very common. Like for instance, I know that there are solutions on the market for PVC for this, yeah, where somebody invested, a customer invested a lot of money in developing first principle models for PVC because it's a bulk chemical. There are many of them. Yeah, so it's worth to spend a lot of money and time to build these kind of models. But if you have a reactor where you have so many different products and you switch on and on and on again, can you do that for every product? That's the big question. Yeah, so you have to find a little bit of trade-off between the complexity and what the payback is. Yeah. So keep it simple. It's always been a very good approach in the APC world, and I think also here it's a very valid approach. Yeah. So if I compare it again to the previous one where I say push to the limits and then everything will be fine, you have a different story here. Huh? So you push to the limits, yeah, and then you see here that the quality is above what is acceptable. Yeah. So that means that there is somewhere a milestone where you say, no, I have to not push anymore to the cool constraints or the heat constraints, whatever. I have to back off a little bit because that will bring my quality back into the specs. Yeah. And in order to do that, you need a whole different kind of technology. Yeah. And that's what you see over here. Yeah, this is a batch recipe. Yeah, the feed flow, and this is a fed batch. Yeah, where you see that we started decreasing the batch time. Yeah, so it's faster and faster and faster. You see feed changes. It's not that strict like over here. It's a little bit higher than the set point. Yeah, so and you can finish earlier, provided that you know exactly what to do in order to guarantee the quality. We have had situations where the customer said, well, we pushed to whatever we know, to whatever we could based on the knowledge that we had, but we see that in our paint, polyacrylate, there are granules that appear in the paint, yeah, and that's completely unacceptable. Yeah, and then the question is, okay, what should we have done during the batch to prevent that? The answer is no clue. Yeah, and then the only thing you can do is slow it down based on engineering feeling, and until the granules are gone. And of course, if somebody would have known the relationship between the behavior and these granules, then we would go to the real limit. But now, if it is not known, you say, okay, let's slow it down a little bit until that magic thing that happens, that we don't want, is gone. So it's one way to look at it, but it's not optimal, but this is reality. And the last point, and then we finish, is of course learn from the previous batch to optimize the next one. So a couple of assumptions, of course, is that the next one should be very similar or the same as the previous one. That's a no-brainer. But what is less trivial is the fact that you know what the previous batch did before the new one starts, and that's a problem. Because, for instance, for PVC, the end quality, which is important, is only after your drying, extrusion, and so on and so on. So only 12 hours after the batch is finished, somebody can tell you, okay, you did a good job. And of course, what have you now learned for the next batch, which probably also already has finished? So as long as you make the same grades, you can keep on reusing that information. But if after 12 hours, you know what you have done, and in the meantime, you're producing a completely other product, that information is almost useless, unless perhaps you can reuse it in 5 or 6 days when you make the same product, assuming you are working under the same conditions. And of course, then you still need to know what kind of handles to play with. You still need to know the quality was bad because, and then something follows. The temperature was too high. The temperature deviation from the set point was too big, or we had an overshoot, or the rate of change, or whatever. So somebody has to give you a handle to say, okay, I'm going to give you a certain limitation for the next batch, and if you comply with that limitation, then rest assured, end quality will be good. So, and somebody has to tell you, or you have to find it out yourself. But that's very critical. And of course, if it's only one handle, it's quite easy. You can just put in the recipe manager an extra constraint. You can do something in the PIDs. I don't know. You can do. You can quite easily implement it. It's in fact a very slow P or even I controller that every time, for instance, lowers the maximum temperature a little bit based on quality measurements. So it's quite easy to implement. Of course, if we have 5 handles to play with, that's a different story, because which one we are going to play, what's the sensitivity, you have to do sensitivity analysis and so on. So that's a very complex formulation that you have to find. So interbatch is very powerful under certain assumptions, and if you know what kind of handles you play with, have to play with. So I have, for instance, you run the batch, you optimized it, the quality is okay, and then you apply an interbatch controller, which you say, well, the quality here was too good. It cost me too much energy. So you know what, I'm going to do something in such a way that the quality is just at the threshold. But I consumed less energy, or I can do it faster, or whatever. So that's a good one. Of course, if you have off spec, like this, you are off spec. What can you learn for the next recipe? So for instance, feed slower, use less, do everything much slower, so that, for instance, your quality is again at the threshold, which is acceptable. This is not sellable, this is sellable. Good. So that are the different ways how you can optimize batches, and you see everything is connected. So you have the PID tuning, the PID design. You have the OEE, and where you can then really measure, have I done a good job, yes or no? So you have to look at it from multiple angles. What I always would suggest is go for a study to design the perfect roadmap. Talk to operators. How many products do we have? How many reactors? Which products you make on which reactors? With which products you have issues? Which other ones you don't have issues? Assess the current control performance, your temperature control, your quality control, your golden batches, and so on. Start with the base layer. If the design is okay, then at least look at the tuning. perhaps do some better tuning or a little bit more better design, split range control, the disturbance rejection, and so on. And then you can make a plan for the next step if that's worth the investment. APC, full-blown nonlinear, linear, and so on. Implement something that keeps track of your performance, like things like OE systems and so on. And then you have a good approach to optimize your batch reactors. And benefits can be really huge, and especially, well, I think if we can say that margins typically in specialties are higher than in bulk, I think that's quite a reasonable assumption. And if you can speed up your reactors and improve quality and so on, I think it's really a good return on investment. But you have to think about many things before you jump into this. Well, adventure is perhaps negative, but it's fun and it generates a lot of money. Good. Andre, do you have questions?
Great. Thanks, Christian, for the presentation. Well done. I'll be opening the floor for questions now, and I'll start from the top. For the questions we cannot get to due to time constraints, those will be responded to by email.
Yeah, sure.
Yeah, that's correct. We have a question here about access to the presentation of today. So this session is going to be automatically recorded, and all attendees will receive a link in the coming days to a recording of this webinar as well as the slides. We also have a question here from an attendee in Qatar asking what are good estimates for the amount of batch reactor time reduction with APC?
Oh, as I said, it's not very easy, but based on the limited information that I have for full-blown APC and so on, I think if think about 10% reactor time reduction. I think sometimes it's 8, it can be 12, can be 13, but 10-ish%. So a batch of 20 hours then can be reduced to, for instance, 18 hours. I think that are numbers you can think of. Reducing it by 50%, I think that should be quite crazy, but 10% is quite reasonable. So I think that's good assumption to assume. If that happens, if I can reduce my batch with 10%, what would be the impact on production, and so on and so on. And that is a good initial exercise that everybody as end customer can do to say, okay, what would the thing bring to me?
Okay, great. Thanks, Christian.
So the whole answer was gone?
I think your microphone might have got it, but
I don't know if, well, it seems that I was muted, so I don't know if what I told somebody heard that. Please let me know. Well, to summarize it into one sentence, think about 10% reduction if you use a full-blown APC.
Very well. Thanks, Christian. We also have another question here from the United States saying, can you predict the benefit of an APC prior to installation?
That's a very tough one. That's really difficult because well, it depends. So if you say, if it is in the type where you say, let me check, there's one over here, run as fast as possible. There you can do it because you know what cooling capacity remains. You can make assumptions on how much closer you can get to that cool capacity, and that you can translate in production and so on and so on. But so based on a couple of assumptions, with this system you can make guesses. If it is linked to quality, then it becomes a completely different story because you need to have that relationship between what am I going to do and will it impact my quality. Assume you can't do anything, otherwise the quality is bad. How do you know that? So I would say for these kind of things, yes, the one you see over here, cool capacity. If for the full-blown nonlinear, I think you can only live with or start by saying, well, assume 10% and what would it bring? And nobody guarantees 10%, 5%, 15%. So I think for the second type, without quality models, it is very difficult. You can do, of course, a full-blown study where you're going to analyze first if you can find these models, and that's a different story. But then already a part of the project is done. Yeah.
Mhm.
So.
Okay, great. Thanks, Christian. We still have a couple of minutes before time runs. We have a question here from France saying, do you integrate these optimizers with, for example, the recipe manager?
Oh yeah, that's what you can do, especially if you have many products. Yeah, it is good that you use your recipe manager to change models, to change constraints, because every APC, then even if it's a full-blown nonlinear, will have a different model for every different product and recipe. So and then you have to load into the APC new models, new constraints, and so on and so on. So yes, you can, in fact, you almost have to integrate it with your recipe manager to make it smooth, because otherwise operators, every time they switch to another product, they have to do too much manual work. Yeah, but that's perfectly doable. So
okay, very well.
Good.
Yes. Well, thanks again, Christian.
You're welcome
for the rich presentation. On behalf of IPCOS, also thank you to the entities for your time. We hope this webinar has been insightful for you all. As mentioned, emails will be sent to focusing on the recording as well as the slide pack, and you should get that in the coming days.
Okay.
Have a good evening, and see you in the next webinar. Thank you.
Okay. Thank you very much, everybody. Have a nice day. Bye-bye.